Hi guys, today I want to talk a little bit about why substances are radioactive. So we've talked a little bit about the different types of radioactivity. We said that there's alpha, beta, and gamma radioactivity. And we talked a little bit about defining the different terms, so radioactivity versus radiation. You've seen a little bit about calculating half-life. And now I want to talk a little bit about why fundamentally things are radioactive. So why things are going to be emitting these high energy particles or energy. And the name of the game, really, what it comes down to is that an unstable nucleus in something that is radioactive, something that is radioactive has an unstable nucleus, and that unstable nucleus is going to do what it can to try to become stable. So in doing so and trying to become more stable, it's going to emit either high energy particles like alpha particles or beta particles, or it'll emit radiation like gamma radiation. So that's kind of the name of the game. You have something that is unstable becoming something that is stable. And there's really two competing forces that are at play when we're talking about radioactive substances. Electric repulsive force and strong nuclear force. So let's start with the electric repulsive force. As the term implies, electric here refers to the fact that we have charged particles. So when we have a nucleus here, here's my nucleus. This nucleus has a bunch of positively charged protons in it. And you can't see that at all. Thanks, marker. Let's try this one. Here's my nucleus with a bunch of positively charged protons in it. Now, we know that if we have a bunch of positively charged things, the natural implication or the natural tendency is for like charges to repel. And we know that opposite charges attract. So we have a bunch of positively charged things in a fairly small amount of space. And so the natural inclination for these positively charged things is to move away from each other. Now the neutrons in here, so the neutrally charged particles, kind of help to keep these things stuck together. But ultimately, as we get more and more protons, so a greater atomic number, as we're going down on the periodic table, we increase the atomic number, which is the number of protons in the nucleus, then the electric repulsive force becomes more of an issue. So that's the thing that's trying to tear the nucleus apart, and that leads to instability. So if we have an unstable nucleus, it's usually a larger one. Most of the radioactive elements are the ones that are further down on the periodic table. Uranium, for instance, is number 92 on the periodic table, so it has 92 protons in the nucleus, and all of these protons want to get as far away from each other as possible. So that electric repulsive force is really trying to pull that nucleus apart. Now, on the other hand, this kind of competing force against electric repulsive force is strong nuclear force, and this is the force that holds the nucleus together. Now, strong nuclear force is one of those things that we know works because we know a nucleus sticks together, but we don't quite understand all the details about why it works. It's one of the forces that governs our universe. When you learn about physics, and if you've ever taken a physics class, then you learn that there's some overarching forces that govern the universe. One of them is gravity, and another one is strong nuclear force. And strong nuclear force is the one that holds the nucleus together. And again, we know how it works. We don't necessarily know all the nitty-gritty details for why. Now, because this is a force that holds together these positively charged particles and our neutrons, then it works better when there are fewer of them. So if I have fewer positive charges in a small space, then that's easier to hold together with strong nuclear force than if I had 92 of them, say, like in uranium. So strong nuclear force really has more of an impact when the nucleus is small. So we have these two forces, they're competing against each other, and they kind of lead to this idea that a nucleus can be unstable under certain conditions, and it's going to try to do things to get to be more stable. And one of the things that it tries to do is to emit high energy particles like alpha particles. And we call that process radioactive decay. And we defined that term before. So radioactive decay is the process of emitting these high energy particles or radiation in order to get to a more stable configuration. So let's say, for instance, that we have uranium-238. That's a fairly common isotope of uranium. And in a nucleus of uranium-238, and I'm just going to represent it as a circle here, in my uranium-238 nucleus, I have 92 protons. And I know that I have 92 protons because that's the atomic number of uranium. And so if I take the 238, my mass number, and subtract my 92, which is my atomic number, I end up with 146 neutrons. So in this particular nucleus, I have 92 protons, 146 neutrons. Now, uranium-238 is not incredibly stable. It's more stable than some radioactive isotopes, but uranium in general likes to break down. And one of the ways that it can do that is by ejecting an alpha particle. Now remember that alpha particles are a helium nucleus, so there are 2 protons and 2 neutrons. So my alpha particle, when that uranium-238 emits an alpha particle, that means it is emitting 2 protons and 2 neutrons. So what I have then is a nucleus that is smaller, and smaller usually means more stable. And so I have 2 fewer protons, so I have 90 protons now, 2 fewer neutrons, so I have 144. And now I've gone from U-238 to a completely different element. Now I have 90 protons in my nucleus, which is a unique characteristic to a different element. I'm not uranium anymore. So if you look up 90 protons on your periodic table, then you'll see that the element you have become is thorium, TH. And the isotope of thorium then is going to be, I'm looking at mass numbers here, if I add together my 90 and my 144, then I end up with thorium-234. Okay. So now, if my thorium-234, which is also another element that is not incredibly stable, if my thorium-234 emits an alpha particle or ejects an alpha particle, now I lose another helium nucleus. Now I end up with a nucleus that has 88 protons and 142 neutrons. So I lost 2 protons, 2 neutrons, and if you look up on the periodic table what 88 protons is, then you'll find that it is radium, Ra, radium. Radium is one of our alkaline earth metals. Okay. And this will continue until it reaches a more, and the isotope here is 230, radium-230. And so this process is going to continue. It's going to continue to eject an alpha particle. It's going to continue to radioactively decay until it reaches a more stable configuration. And there's specific magic numbers on the periodic table, and that's actually the way that they call them, magic numbers. And one of these magic numbers is actually lead's value. So if you look at lead on the periodic table, lead tends to be a pretty stable configuration, which is not to say that lead doesn't have radioactive isotopes. It just tends to be more stable. You can also find other stable configurations with smaller numbers of protons, smaller atomic numbers as well. So this process is going to continue. Now if you look at this, I am literally changing from one element into another. So I am this element here, I'm uranium. I'm incredibly unstable, so I eject an alpha particle, and now I'm a completely different element. And then this one's unstable also, and so now I'm a completely different element. This process is called transmutation. Now, we usually look at the word mutation and think about radioactivity and think about bad things, right? Like mutation of DNA, for instance, which causes things like cancers and all sorts of problems with creating proteins and all kinds of things. So mutation is usually a bad thing, but the term mutate or mutation in general just means changing. So we're just changing from one element into another through the process of radioactive decay. Okay, and that's transmutation. And transmutation is the major way that an unstable nucleus will become more stable. So we aren't stable in our current configuration, then we're just going to start ejecting things off until we reach a more stable configuration, or stable magic number, if you will. Okay, so this is kind of the process of why things are radioactive, the different forces at work, and we'll talk a little bit more about how we can harness this process in our next video on fusion versus fission. Alright, if you have any questions, don't hesitate to ask, and I'll talk to you guys again soon.